We will deal a lot with vectors in this class. So we need to talk about the notation. How do you symbolize that there is a vector? And there are a couple of different methods of doing this. So if I have some vector A, I can write it as a vector like that. When I'm doing word processing, this is the arrow I naturally pick. I guess if you're using OpenOffice, that's the one that's the default. If you're using Microsoft Word, then you have a choice of different ones as long as you can find it. They hide them in various places. Anyway, I hate Microsoft in case that wasn't obvious from some of the videos or other things I've done. I can also express it as like this. This is what I call the half arrow. This is the way I represent it in class. Please note that just because I drew the arrow that way does not mean the vector is pointing in that direction. That's just the symbol over the A. Another method that I do sometimes is the double print. I actually do this for one vector particularly for some unknown reason, presumably childhood scars. When I deal with the resultant, I do what I call the double print. Also, taking notes, sometimes this is a little bit easier taking notes, but that represents a vector. And then textbooks sometimes will do boldface, and I hope you can understand why I tend not to draw the boldface, but boldface is another way of representing the vector. So that's just the basic generic notation. So this would be vector. Now, magnitude of the vector, in some cases called the strength. So if you're talking about the electric field strength, that is the magnitude of the electric field. Magnitude, size, sometimes used. I'll put strength down, amplitude in some cases. These are more specific. There are specific cases when you use those. Magnitude tends to be the dominant word there. Typically, what you're doing is you're taking the vector and you just put absolute value symbols around it. Now, some textbooks will put sort of the double absolute value symbols around it to represent it, to differentiate magnitude from absolute value. I don't do that, but just recognize that sometimes you will. And also, we can just write it without the vector symbol, and this would represent the magnitude of vector A, assuming vector A has already been defined. There are some issues with that, especially if you're talking about distance versus magnitude of displacement. The symbol for distance traveled is delta x. That is the distance traveled. Displacement is delta x with a vector symbol over it. And distance is not necessarily the magnitude of the displacement. So if I'm talking about magnitude of displacement, I really do need to do it that way. So this would be magnitude of displacement, and this is distance. And I believe it's a lab question or test question, old test question or quiz question. At some point, somewhere out there, there's a question about when are these actually the same. So just be aware of context and that there are eccentricities, of course. There are times in which I feel that physicists do this just to weed out those who don't know what they're talking about. Now, if I want to represent a vector, the three major forms, I guess, we have polar form, rectangular form, graphic form. For rectangular form, we establish these things called unit vectors. A unit vector, it has to have a magnitude and direction, because all vectors have a magnitude and direction. The magnitude is 1. There are no units there. It is unitless. And the direction is usually what I say it is. So this allows you to redefine the coordinate system. In math class, there's so many times where this is the x-axis, that's the y-axis, and you can go with horizontal, vertical, but frankly, there are many times, especially when we get into Newton's laws, that if you stick with a horizontal, vertical paradigm, you're going to basically quadruple the amount of math that you have to do. So there are times in which that is not convenient. Now, because x and y, horizontal, vertical, have been so ingrained, it is usually convenient to come up with a different set of letters. And so the classic letters for rectangular form, we establish I hat, J hat, and then K hat for a three-dimensional problem. So first off, let's talk a little bit about 3 dimensions here. Now, I have a 2-dimensional piece of paper and I need to represent 3 dimensions. There's the forced perspective, or the perspective point of view, where you can do sort of X, Y, Z axes. But another way of doing it is to represent it by dots and X's. So if you imagine an arrow coming at you, what you see is the point. And so this would represent out of page. or going that direction. If the arrow is going away from you, you see the feathers, and granted, feathers on an arrow don't look like that or shouldn't look like that, but this is just the memory trick here. This means, so you're seeing the feathers, it's going away from you, so this is away from you or into page. So that's why I put a dot there and I circled it, because otherwise it's difficult to see the dot to recognize the K direction. Or I could have I hat going this way, J hat going that way, K hat coming this way. And just to give you an idea, J has to be perpendicular to I, K is perpendicular to the two of those. The direction of the J hat relative to I hat, it really doesn't matter whether I put it that way, or you basically have 360 degrees in which I can put it as long as it's perpendicular to I hat. K hat, on the other hand, it is set. There's something known as the right-handed coordinate system. And for the right-handed coordinate system, I cross J equals K. We will get into cross products a bit more later, but because cross products really come into play when you start getting into rotational motion. But to define a right-handed coordinate system, I cross J is K, and the way you would do the cross product is you put your hand in the direction of the first vector, the I hat. You want your fingers so that they bend easily towards the second vector. So J hat's over here, so I put my hand like that. My fingers bend towards it, and my thumb points in the direction of the third vector. So I cross J is K. This defines the right-handed coordinate system, and this is why K is up out of the page. If I had I going this way and J going that way, well, I put my hand in the direction of I, but my fingers need to bend so they bend towards J, and my thumb points in is now pointing away from the camera, so K is into the page. And more detail later. One comment about the thumb points in the direction of it. I've had some people get really messed up because they can bend their thumbs way back, whatever the genetic mutation is for that. This is, again, just a rule for it. I, J, and K need to be perpendicular, so even if I can bend my thumb so that the tip of it's pointing directly opposite my fingers, that does not mean the vector goes in that direction. So I cross J is K, or let's say I had I going this way, J into the page. So I cross J, because I want my fingers to bend towards the other vector, and since J is down, I want my fingers to bend down, and then K points to the left. K would be in that direction. Now, if you are left-handed, you still use your right hand. I have had left-handed students in the past where what they do is they use their left hand, and then they know whatever they get is the opposite of the right answer. I believe that works fine, but what I've also observed is there's going to be a point when you start to get an intuitive sense for what it is, and then you use your left hand, and there suddenly begins this switched coding where you sort of do a double negative, and it starts messing up. So if you can try to keep the habit of using your right hand the entire time, then I think life will be a little bit better for you in the long run, as long as you're pursuing this. If you end up wanting to be an English major, like my daughter ended up being, then yeah, just do whatever. The shame of it. Oh, anyway, sorry. That's a different note. So, rectangular form. Since they have a magnitude direction, if I have a vector that's pointing like that, and I establish my coordinate system, I hat, J hat, and let's see, let's make this a 37-degree angle, make that 5, so therefore that's 3 and that's 4. I picked that so I'd get a 3, 4, 5 triangle. So this is 5, 37 degrees. That is polar form. That can also be written slightly differently. We'll get to that in just a second. But that's also 4 to the right and 3 up. So this is 4 meters I hat plus 3 meters J hat. That is perfectly acceptable because I define my coordinate system there. Or I could have just defined I hat to be in that direction. So let's do it separately over here. So I have my 5 meters here at a 37-degree angle. And I'm just going to define I hat to be in that direction right there. And so it's now 5 meters I hat. And that's also acceptable. I've defined my coordinate system there. Typically, if you've got you would do this if it ends up just being a one-dimensional problem, or yeah, we'll get into those issues later. Or some people just still like the horizontal and vertical. You can do it that way. The graphic form is you're just drawing it. It is assumed that the angle here is always based upon 0 degrees being that way, and then going counterclockwise or positive angles, counterclockwise or negative angles. So 37 degrees is going to be somewhere like that. And you have some scale where that would represent 5 meters, 37 degrees. And so we have the same vector expressed in rectangular form, polar form, and graphically. In terms of polar form, there is, when you get to circular motion, sometimes it's helpful to think of it slightly differently. And so I'm going to introduce another unit vector called r hat. This is a radial unit vector. This one is a little bit narrower in definition than I hat and j hat. So radial unit vector. The magnitude is still 1, but the direction, so the magnitude of r hat is 1, and then the direction of r hat is away from center. Now perpendicular to that is theta hat. So if I took my 5 meters and 37 degrees, which I express in polar form as 5 meters 37 degrees, I can do it with the unit vector notation as 5 meters r hat plus 37 degrees theta hat. And so that would be sort of the polar expression using unit vector notation. There's a derivation we do for centripetal motion where this becomes much more convenient. And I think that is it for notation.